Outcome 4, Component 4, Part 1, we're going to talk about graphing inverse functions. Now, before we get into actual problems with inverses, we want to talk a little bit about what the heck an inverse function even is. So, mathinsight.org defines an inverse function as a function that undoes the action of another function. So, a function g is the inverse of function f if whenever y equals f of x, then x equals g of y. What do you notice happens here with your x's and y's? Hopefully you notice that when I'm looking at two inverses, if f and g are inverses, it's flip-flopping the x's and the y's. In other words, applying f and then applying g is the same thing as doing nothing. We can write this in terms of composition functions, which we've seen in our previous lessons. So what we would do is take g of f of x, so we're plugging f of x into g. If f and g are inverses, then this should equal x. When we're talking about inverse functions, we will denote this by using f with a little -1 as that exponent. This is what we call f inverse. So anytime you are finding an inverse, you want to make sure you put the letter with that little -1. If you were finding the inverse of g, you would say g with that little -1. This means the inverse of g, or g inverse. Now, as we go through this component, there are two things that we will be asked to do. The first thing is we will be given a graph of f of x. We will need to graph its inverse and then determine if the inverse is a function. The second thing that we'll do is we'll be given f of x, so we'll be given a function and we will find its inverse. Today we're going to focus on this first bullet point here. They're going to give us a graph, we will find its inverse and determine if that inverse is a function. So when we are given the graph of f of x, to graph its inverse, we are going to follow 3 steps. The first thing that we'll need to do is look at the graph of f of x and find nice ordered pairs. So I'm going to say find nice ordered pairs. By ordered pairs, I just mean we're looking for points on f of x. So I'm looking at just the function that they give us. We're going to write down some nice ordered pairs. Once I have those ordered pairs, we are then going to switch the x's and the y's. So we're going to flip-flop our x and our y's. Once I have those new points, I am now going to graph the new points and draw in the inverse of f. So what's kind of tricky about these is that the equation that they give you each time might look a little bit different, but regardless of what that equation looks like, we are always going to follow these 3 steps. Find some nice points, switch the x's and y's, and then graph those new points to find the inverse. Let's go ahead and take a look at example 1. It says the original function f of x equals -x squared minus 2 is graphed below. So this graph that they give us right here is f of x. That's my original function. We want to graph the inverse of the function, so eventually I'm going to graph on here. And then I need to identify the domain and the range for both the original and the inverse. So we're going to follow those 3 steps that we listed above. The first thing that we'll do is look at our original function, and we want to find some nice ordered pairs. So I like to start with just putting dots on points that I think look nice, so they're falling just perfectly on an intersection. Once you have about 4 or 5 points, that should be enough. So it looks like I have 5 here. I'm going to write these down. This one farthest on the left was at -2, -6. My next point is at -1, -3, and I recommend just writing these vertically. Oops, should be -3 and -6. So what we're doing here is keeping all of our x's in a vertical line and our y's in a vertical line as well. I also have a point at 0, -2. I have a point at 1, -3. And I have a point at +2, -6. Now all of these first points here came from my original. These are points coming from f of x. Our job is to find the inverse, so I'm going to label these points as the inverse of f. Notice I'm using that little -1 there. And all I need to do here are take my points and just flip-flop the x's and the y's. So instead of -2, -6, I'm going to have a point at -6, -2. Again, flip-flopping, I have -3, -1. I have a point at -2, 0, -3, 1, and -6, 2. Just taking those x's and y's and flip-flopping. I'm now on to step 3. For step 3, what I want to do is take my new points and graph these on my graph over here. So I'm going to go to -6, -2, -3, -1, -2, 0, -3, 1, -6, 2. We're going to go ahead and connect. And this graph here is my inverse. Now there's a few things you can look for when you're graphing this inverse. The first thing is that shape should stay the same. This was a parabola. When I graph that inverse, it is still looking like a parabola. If you end up with kind of a weird looking shape, it probably means that you wrote down one of your points wrong or you didn't flip it correctly. Another visual way to check this is you graphed the inverse correctly is to think about the line y equals x. So I'm going to graph this line y equals x in blue here. The line y equals x is just a straight line. It starts at 0, 0. It has a slope of 1, so it just goes diagonally this way, and it would go the opposite way as well. What happens when we're finding inverses is our original function is reflected over this line y equals x. So I like to draw in that line there and just kind of visually check to make sure that it looks like this graph was just flipped over that line. Once we have that inverse graphed, we're then going to look at both functions and write the domain and the range. So looking at f of x, that was this graph that was given to us here. Domain means I'm looking at my x's. Now as I look at this function, it looks like it's just kind of stopping here on the left-hand side, but technically this is going to continue on and on and on and on to the left forever and ever. There's no stopping point as we go to the left. The same is true as we go to the right-hand side. It looks like it's kind of stopping at 3, but it's really not. It's just going to keep going out, gradually getting wider and wider. So there's no restriction on going to the left or to the right. So my domain is all real numbers. Range means I'm looking up and down, so I'm looking at y values. It looks like both of my arrows are pointing down, so these ends are going to continue downward forever. But it does look like there's a stopping point as I move up my graph. I'm noticing there's kind of a top or a maximum at this point here. There's nothing above the y value of -2. So if my graph is all below -2, I'm going to say that y is less than or equal to -2. Okay, switching gears, we're now going to look at our inverse. Remember, that's this one that we drew in, so that's my pink graph here. Again, domain means I'm looking at x's, so I'm looking horizontally, I'm looking left and right. Looks like my arrows are pointing to the left, so they're just going to continue going left, left, left forever and ever and ever. But it looks like there is a stopping point going to the right-hand side. It stops right here at an x value of -2. There's nothing to the right of -2. It's all to the left. So to show that it's all left of -2, I'm going to say that x is less than or equal to -2. Range, again, looks at y values, so I'm looking up and down on my graph. Although it looks like this might be flattening out, technically this parabola is going to continue to move upwards. It's going to be very gradual, but it's continuing to move up, and it's continuing to move down. There's no restriction, no stopping point, so my range is all real numbers. Okay, what do you notice about the domain and the range of f of x and the inverse of f? So I'm looking here, it looks like my domain was all real numbers for the f, but then the inverse, the range was all real numbers. For the range we had less than -2, and look what happens here, the domain is also less than -2. So when we're looking at the domain and range of the inverses, your domain and range will always switch. So domain and range switch. One thing you do want to make sure you're careful of is that when you're talking about range, make sure you have a y value. Even though it's now switching over here to x, or to the domain, we do need to make sure we have an x there, because domain always, always, always looks at x's. Okay, if you recall all the way back to Algebra 1, you learned that an equation is considered a function if every x value has one and only one y value. If we know what the graph looks like, there's a really nice visual way to tell if the graph is a function, and the way that we'll do this is to use what we call the vertical line test. Okay, the vertical line test says that if I draw a vertical line, and vertical means we're looking up and down, if I draw a vertical line through the function and it passes through only one y value, so it crosses my function only once, then it is a function. If it crosses more than once, then it is not a function. So here's two quick examples. If I gave you this little parabola here, and I were to draw in a vertical line, I can draw this vertical line anywhere that I want. How many times does that vertical line cross my parabola? It only crosses it once. Now maybe you're like, Mrs. Soto, I don't want to draw it at -2. I want to draw it way over at 3. Sure, you can draw it over here at 3. Guess what? It's still only crossing one time. No matter where you put that vertical line, it's always going to cross the graph once. Because it crosses one time, it means it is a function. If we look at our next example here, we've now taken our parabola and kind of flipped it over on its side. If I were to draw in my vertical line this time, it is now going to cross, it looks like, 2 times. Again, maybe you want to draw it way over here. Still crossing twice. If it crosses that function or that graph more than once, then it is not a function. Hey, be careful here. There is a spot where you could draw it so it only crosses once, but if there's any spot where it crosses more than once, then it is not a function. Go ahead and take a minute to try example 2. You are given two graphs and you want to determine if it is a function. Okay, hopefully you notice that both of these are indeed functions. When we draw in those vertical lines, it is only crossing one time. Okay, let's go ahead and put everything that we've learned together in example 3. So in example 3, they give me f of x. They tell me the original function f of x is this line here. So this guy is f of x. We're going to put everything together, so we want to graph the inverse, find the domain and range, and then finally determine if the inverse is a function. So again, I'm going to start with finding some nice points on f of x. There are tons of nice points here. You just need to find, like we said, maybe 4 or 5 of them. I'm going to go with those ones. So these are my points for f of x. I have 0, -5, 1, -3, 2, -1, 3, 1, and 4, 3. Okay, when I'm finding my inverse, I'm going to take these points and flip-flop the x and y. So I have now -5, 0, -3, 1, -1, 2, 1, 3, and 3, 4. We'll go ahead and graph those. So -5, 0, -3, up 1, -1, up 2, 1, 3. Starting to see the pattern here. 1, 2, 3, 1, 2, 3, 4. Okay, once I have my points, I can go ahead and sketch in. And I like to label, so I remember this one here is my inverse. Okay, looking at my original function, just f of x, so that's this one here that we have in black. We want to list the domain and range. Remember, domain deals with x values, so I'm looking left and right. It looks like there's no stopping point as I'm going to the right. This is just going to keep going up and right forever and ever. And this side's going to keep going down and left forever and ever. No restrictions, no stopping points. So my domain is all real numbers. Range looks at y values, so I'm now looking up and down. It looks like it's going to go up forever, and it's also going to be moving down forever. No restrictions, so my range is all real numbers. Okay, looking at my inverse, I'm going to look here. Again, domain is x's. It's going left and right forever and ever, so all real numbers. And up and down for my y values. It's not going up as much, but it's still moving upwards and downwards, no restrictions. So all real numbers. Okay, I'm going to add a few things onto my graph here. Again, I like to visually check that this is in fact the inverse just by drawing in that line y equals x. So I'm starting at 0, 0, and just going up 1 over 1. Okay, does it look like we took this black graph, flipped it over on that blue line? It does look like that. It does in fact look like a reflection, so I think we're good with that inverse. Okay, and the last part here says, is the inverse a function? So I'm checking to see if the inverse here is a function. So when I'm looking at my graph, I know there's a lot happening. I really want to be focusing on this inverse. I'm focusing on the pink line here. To determine if it's a function, we're going to use our vertical line test. So if I were to draw in a vertical line somewhere, how many times would that vertical line cross the inverse? Well, it would only cross it one time. So this means that the inverse is a function. So we'll say, yes, the inverse is a function. And for our explanation, we just need to say that we used the vertical line test and it only crossed once. So I'm going to say, yes, the inverse is a function because it passes the vertical line test. Your explanation might look a little bit different than mine here. You could say that the inverse is a function because when I drew in the vertical line, it only crossed once, but make sure you're saying something about how you used this vertical line test. Go ahead and try example 4 on your own. Once you're done, you can go ahead and play your video to look over my work and check your answers. Here is my work for example 4. Again, I started with looking at f of x here, found some nice points and jotted them down. I then flip-flopped each of those x and y values to get my inverse of f. I graphed that inverse of f. Hopefully that inverse looks familiar. That's a cube root function. The domain and range for both the f of x and the inverse of f were all real numbers, no restrictions as you move left and right or up and down. And then again, when we're finding if the inverse is a function, we're looking at that vertical line test. I drew my vertical line right here in green. It only crossed the inverse one time. So I said, yes, the inverse is a function because it passes the vertical line test, meaning that that vertical line only crosses the inverse one time.